All right, so what we're going to be doing today is we're going to be talking about 3D digitization. We're going to talk about why we digitize, how we digitize, and then the different methods that we can digitize objects and how we choose to go down those different paths. Then we'll talk about the results and applications of 3D digitization, and then how you can apply 3D digitization to your work. So 3D digitization, what and why? Well, it can be used in just about every discipline you can think of, starting with cultural heritage, natural history. One of the ones I work with a lot is medicine and anatomy and engineering. And then I've seen other people do a lot of GIS and archaeological stuff. So why do we digitize? Well, it's part of digital preservation, which supplements physical preservation. You do it for rare and valuable collections, time-varying structures, things that may change over time, whether it's from human traffic or maybe it's something that's out in the wild and it's being eroded. It enables novel research. You can analyze properties of objects once you get them into the computing system. And it gives you easier access and broader dissemination for research, teaching, and community engagement. Thank you for joining us, sir. I don't really care for this particular reason why we digitize, because it's like the foreboding one, but you also want to digitize and preserve some of your collections because they may get destroyed by fire or some kind of terrorist act, maybe war. Now we're going to talk about the how. This is where I'm going to focus most of our talk today, is because it's really what I do in 3D digitization support. So this is a flow chart that we created for when this person wants to digitize something. And every time somebody comes to us and they want to digitize an object, we have this flow chart in the back of our mind because we will follow this flow chart to determine what is the best route for digitizing your objects. So I don't know what my next slide is. Okay, good. Oh, it did turn green? Okay, good. So the first step in this flow chart is whether or not we're actually going to digitize the object that you brought to us. Sometimes people who don't have 3D modeling capability will come to us and they'll say, hey, I want to scan this, because they view scanning as the easier route to get that object into 3D, but that's not always the case. Take this example here. This was a microscope lens holder, and the client wanted to make the lens a little bit longer because he was going to refract light differently in there. I really don't know what he was doing. He asked me to scan it. I showed up with the scanner. I could scan the object, but by the time I've scanned it and turned it into a 3D printable model, it would have taken me hours. Instead, I took a pair of calipers to it, measured it, created a profile out of it, and swept it into a already parameterized model that he could go ahead and change the dimensions in any direction he wanted. And this took me, 15 minutes of measuring time, probably 45 minutes. I did it in an hour, let's just put it that way. And there's no digitizing method that would have made that go faster. I don't use a keyboard, I use the screen. I'm not used to this. But let's say it's an object that you obviously can't model, and let's say that it's an object that you need to know what's inside of it. You need the interior data. That's when you want to use volumetric methods, such as CT scans or MRI scans. And I will give you some examples here of where we've done that. We worked with Indiana Institute for Biomedical Imaging Sciences. That is a chargeback system. I don't remember their cost, but I can tell you the clarinet mouthpiece on the right here was scanned for about $500 or $600. Then this surgical guide, that was something that was done on a cadaver. Obviously, we needed to have that interior information. This is an interesting application of volumetric scanning, and that is to improve radiation boluses. So a bolus is this skin-like material they put over the surface of a patient when they're getting radiation therapy. And it's best if that is fitting perfectly over the person's skin, and you don't want to have gaps like you see up here in the old method, because that can cause problems with the doses of radiation. It can cause skin burns, inaccuracies of how they're treating the tumor. So this client of ours came to us and asked us to help him with a workflow for 3D printing bolus material. The good news is he gets the CT scan anyway as part of the radiation therapy. So the data is already there, and we helped him design a workflow that would extract what the dosimetrist designed as the bolus and then 3D print that bolus. And as you can see on the results down here, the bolus fits much more form-fitting to the patient's skull, which improves both the patient's comfort and the patient's treatment. But let's say you don't need the interior or you just want the exterior of the object. Then the next question is, do you want to use a 3D scanner or photogrammetry? And it used to be we always use 3D scanning, but photogrammetry has come so far that we would prefer to use photogrammetry. But there are still some scenarios where we would use, keep going back to the keyboard, that we would use 3D scanning. So let's talk about the scanners that are available. We have structure light scanners. Those are the scanners that we primarily support in the Advanced Visualization Lab. That includes the 3DMD facial system on the right and the GoScan handheld system. We don't support them in Ulta anymore. It's been retired. Next Engines, we just know the workflows. We don't really own one, but they're cheap enough that a lot of people will buy them and then rely on us for assistance. The Matterport system captures large spaces, and that's been something that's been taking off and becoming quite popular. And then finally, the Leica LiDAR system. We don't own one, but we know of a company that will rent one. It's about $1,500 a day, and I'll be talking about a project later on. You're supposed to like shock me when I go over to the keyboard. So I have to, anytime I do a digitization talk, I always have to start with talking about the 3D scanning we did for the collaborative initiative on for fetal alcohol spectrum disorders. And that's because this particular NIH-funded project is what started us into the world of 3D surface scanning. We were doing it for 15 years. We started in 2002, I believe, and we've been to six countries. You see the numbers up there. And we captured over 5,000 subjects over that 15 years. And we were the head of the 3D core. And on the right here, you can see all the researchers and collaborators, except me, because I'm not important enough to be in that picture. No, I didn't take the picture, but I've traveled with half those people. In fact, the gentleman here on the right, he's the guy that first diagnosed FASD back in 1972. So I'd like to go over a few example projects, and I'll be doing this for photogrammetry as well. These are projects where 3D scanning is definitely the superior method over photogrammetry, mainly because of the speed and the scale accuracy. So the swim trainer you see on the top right, that's an engineering project. And even though the mesh is red and the original swim trainer was red, we did not scan that in color. And we scanned that in probably about 45 minutes. And the whole idea there is that it's a broken swim trainer that the swimmers put on their hands, and they don't manufacture them anymore. But the swimming coach up at IUPUI wanted to remake them. So he had an engineering student scan it, and then she mirrored it, and then she was supposed to actually change the shape of it, and they were going to start seeing if they could make the swim trainer more effective. The surgical training improvement down here, you might look at this and you can see these little holes on the shoulder and the holes on the knee. Well, that's the artificial skin they wrap over a surgical trainer. Now, I don't know about you, but I don't want a surgeon that's been trained on something that has holes already done for where he's supposed to put his tools into your body. So the idea here was we would scan this, and then the bolus guy, Brian Overshiner, was going to create real ones that looked like skin, and the surgeon would actually be graded on whether or not he entered the body in the right spot, as opposed to having a cheat sheet. And then, of course, one of the most important ones we've done recently is the digital prosthetics workflows. This is Travis Bellici and his patient Shirley Anderson. And what Travis's dream was to do a prosthetic in a day, because Mr. Anderson waited, I think, 3 months for the traditional prosthetic to be made for him. That includes hand sculpting. Now, while we didn't create the digital one for him overnight, we were able to help Travis with a workflow that he was able to get a patient who was scanned pre-operation and then had his nose removed that day. And then the next day he had a 3D printed nose that he could wear home. Now, it wouldn't be his final nose, but it was something that he could put on his face as opposed to a mask and not being ashamed. And then furthermore, that same data is used to make the final prosthetic. Again, fast workflows. This is an example where scanning is still a little better in photogrammetry, unless you're Matthew Brennan and you can really do really good interior photogrammetry. And this was a LiDAR scan for the digital preservation of the Bethel African Methodist, say it for me, Episcopal Church, thank you. Up in Indianapolis. It's supposedly, I think it was the oldest African-American church in the state of Indiana, and it's been repurposed into something else now. I think it's, yeah, I don't know what they're doing. I can see them building it out the windows, but I think they're turning into hotels, what I've heard. But on the left here, you can see the LiDAR data. And then Zeb Wood and his students created a 3D model reconstruction, and then they texture mapped it based upon photographs of the original data. If you go to the website now, they now have that data available for you to download into VR, or you can just use it, the WebGL version. Look back to the keyboard. So I'm going to talk a little bit about the limitations of 3D scanning, and I really should move this slide. I'm really using 3D scanning as an example of the limitations for all forms of 3D digitization. So this also holds for photogrammetry, and it also holds for volumetric methods. And that is, you have to understand the accuracy, the resolution, and what they mean. So accuracy is the certainty or error, it depends if you're glass half full, glass half empty, at the point of measurement. So this sphere here in this grid shows that certainty error. And then the resolution is how far apart those errors, how far apart those points of measurement are made. So if you kind of look over here at the scanner, think of it as a net being cast on top of the 3D surface you're trying to scan. Now, what a lot of people do is they immediately say, I want the highest resolution and the highest accuracy. And that's not always the case. What can happen when you crank up the resolution and accuracy of any of those methods is you start to get a sandy appearance. Imagine these spheres all bundled up against each other and actual measurement points next to them. You're going to have a very sandy, rough surface. I tried to simulate that with the elephant over here. You can kind of see it's a little sandy. This is 0.5 millimeter resolution. And then down here is 2 millimeter resolution. So you get more details, but at the cost of it getting more sandy. That elephant scan is actually pretty good. I need to get a better bad example. Another limitation of 3D scanning is that it does not capture color as well as photogrammetry techniques. And finally, I have a display big enough that you can see the differences. So this is an owl that was scanned on the left, and then on the right, it was photogrammetrized. And you can see the color difference is just no competition between photogrammetry and 3D scanning techniques. I did it, I hit the keyboard. So now that we're going to talk, now that we've talked about when you don't digitize, when you do digitize volumetrically, and then when you use 3D surface scanning, now we're going to talk about the photogrammetry workflows. Back to keyboard. So software-based photogrammetry is a method for extracting the 3D-dimensional models or measurements of an object from 2D photographs. Now, it has a wide range of applications, and hopefully I will show you all those today. But it does require computationally complex data sets. So the general workflow is you take Ernie Pyle statue that's here on campus, you take about 300 photos of it, you plug it into some 3D, some photogrammetry and 3D post-processing workflows, which are things that we provide for you. And then you get a resulting 3D model that is texture mapped with a high quality color. Getting fingerprints on your screen, Chris. I do need to talk a little bit about the photography part. We've used just about every type of photographic system you can use. We even use screen capture of 3D models. We've even used YouTube videos and just peeled off single frames of YouTube videos for photogrammetry. But the key issue is you got to have quality images. You got to be consistent. Your lighting has to be consistent. And we have worked with, I already said video, but we've used high-end cameras, and I've even had some better results with cell phone cameras on certain objects, which I'll explain as we get to those objects. But it's probably the most frustrating part if you don't know photography that well. You got to learn at least some of the basics, even if you're using your cell phone. So here's the process again. Here's some example projects where photogrammetry was definitely the better tool. We captured some objects. I take that back. I think I actually scanned these at the Ruth Lilly Medical Library, but I know Tassie and her team got the statues on campus, and over here on the right, you can see Herman Wells statue that was photogrammetrized. And you can see the models in blue were the ones that were set up for 3D printing. And then down here, you see a photograph of those actual watertight meshes that were 3D printed. Oh, that's right, it's a big file, sorry. Another example project is the Bicentennial Bus Showcase that we just delivered today. Yeah, you like that. So we did the Showalter Fountain, and Scott Birch, our manager, did a lot of the work here and made it look into a model. This is kind of like our Hope Diamond of digitization. We put a lot of effort and work into this. He actually put some water in there. And then here at the old oaken bucket, the image on the left is the real oaken bucket. And we scanned it and we also photogrammetrized it. We kind of hybridized that data together. And then on the right, you can see the actual prints. And those are actually bronze letters. And that's actually a bronze plaque on the bucket. But the bucket itself is printed out of a 3D colored powder. And then you see two cool dudes that are happy that they're done and the final exhibit. Yes, that was today, yes. That was Scott's idea. Yeah, I think he's trying to turn us all into extroverts or something like that, right? He's all disappointed we're all introverts. Now we got to be extroverts. Yeah, so this is on the test. The idea is it's very complex and it's best if you take advantage of our high performance computing. So let's talk about scalable photogrammetry. And what do I mean by scalable? Well, I mean several things by scalable. One, it's more scalable than 3D scanning technology because everybody has access to a camera. So that's one type of scale. We've had 4 scanners, everybody's got a camera. Another thing that makes it more scalable is that you can do a variety of size of objects. I'm showing you large objects here, but you can do small objects. And yet the third scalable, we should come up with a 3S on this one, like Eric would come up with something. The other thing that makes it scalable is we have the software on our high performance computers, both karst and carbonate, and you can just offload your photogrammetry jobs on the high performance computers and not worry about doing it on your own computers. You don't have to buy any software, and we have the workflows in place and welcome more and more users. We have 100 licenses, and I don't think we've ever used them all at the same time. Tassie's not here to tell me, so. All right. All right. And if you know what you're doing, like Matthew Brennan, you can capture fantastic interiors like what he's done here. And then where is this? It's the chapel by the chapel. Thank you. So, what's that? We're not wearing a microphone. Oh, Beck Chapel? Yeah. Beck Chapel, that's the Beck Chapel. Sorry. And then over here we have Malta Alban, which was a huge photogrammetry project that was ran by Alex Badillo, who I still haven't met. And they flew a drone and captured over 14,000 photos. And I think they did in that case get special request compute time on the high performance computers so that they could compute. Here's some other examples. Gary Motes has done work with a lot of the bone collections that are here, and the Center for Biological Research Collections. My glasses gave out. Then Bernie Fisher's done work for the IU Virtual World Heritage, and this is one that's really cool. Once again, Matthew Brennan did it. He actually took the different phases of an archaeological dig site, and he captured how they dug down into the ground. I like that. Here's one that we just recently did, and that's small objects. So we've gone from the whole Malta Alban, and now we're getting down into macro objects. On the left, we have the e-learning forensics project that we just completed. We're still working on getting a ADA compliant viewer for students that are at home. But we captured several bullet sets, and as you can see, the photogrammetry even picked up some of the 3D data, not all the striations. And then we also captured shoes. The shoes on the left are the real, the shoes on the top are the real shoe. Really? The shoes on the top are the real shoe, colored and untextured, and then on the bottom are the actual cast. And then for fun, when we were starting our macro work, I had this little pinky demon that has, ignore the copyright on the bottom, if you will. I don't know if I get in trouble for that. But we photogrammetrized it with cell phone cameras. So on the left, you have a Samsung Galaxy 4, about a 5-year-old phone. In the middle, you have a Google Pixel 1, which is now probably a 2-year-old phone. And on the right, you have a GoScan 20 data set. So you can see the advantage of photogrammetry over the GoScan system. And the GoScan system is meant to scan things about that size as well. But we definitely got more details and better geometry and better colors out of the photogrammetry data set. So here's the steps of photogrammetry. Most of this is automated for you, but you can do it manually on the supercomputers using ThinLeak, which is kind of like, for those that don't know, it's kind of like remote desktop for Windows, except it's remote desktop into the supercomputing systems. The software that's out in the field, there's a whole smorgasbord of them. I'm not going to go over all these, but Photoscan by Agisoft is the one. Oh, sorry, I need to update my presentation. It's no longer Photoscan, it's now Metashape by Agisoft. That's what we have on our supercomputing resources. Gee, look at the presentation for how many hours, and I didn't catch that. So I talked a lot about photogrammetry, surface scanning, volumetric scanning, and we're going to return to that flow chart. As I said, scanning has the advantage of your object is immediately accurate to scale, and it's a very fast system, but it's also very expensive, and it's a limited resource. Photogrammetry is the most adaptable surface scanning, and it's also, even though it's a slower process right now, it's getting faster and faster. In fact, I think the amount of human hours is mostly, last I checked, on the capture time. So the compute hours is long, maybe anywhere from 4 to 20, 30 compute hours, but the actual human hours is really the amount of time you took capturing your images. And the better job you did capturing your images, then you don't have to do as much 2D post-processing as well. So that's a little bit of who captured the data. Here's some examples, some side-by-side examples of which you would use. So I already talked about the swim trainer. That was a scan project. This elephant here, I did both so that you could see the results from photogrammetry and from 3D surface scanning. I'm just going to ask, which one's scanning, which one's photogrammetry?
Well, based on the owl, the one on the right is the scan.
Give that man a cigar, obviously. Yeah, you can immediately see the color of the elephant on the left is superior to the elephant on the right. But what else photogrammetry does, it's better in our scanners. And when I say our scanners, I mean the GoScan structured light systems. Notice the detail on the tusk here and the detail on the tusk with the scanner. You get higher details on the elephant. And I should mention the elephant on the left has been decimated so that it would be the same as a 0.25 resolution elephant on the right. I think I put him at 0.25. Good question. I'm going to say 200, I'm guessing. I'm the one that did it. That elephant's been photogrammetry. It's gonna melt. We scanned it, and so that one I did, and it was about 200 photographs. And I did spend time masking. I will